Hello students, welcome to the 34th lecture on particle physics. And in the last lecture, we have talked about supernova neutrinos and the formation of heavier elements in the stars. And those were the natural sources of neutrinos. Therefore, we have both natural sources of neutrinos like the neutrinos being produced inside the core of sun or inside the core of a star. Then during the death phase, the neutrinos are coming out, which we know by the name supernova neutrinos. Then we have neutrinos coming from the cosmic rays, which are when the primary cosmic rays are interacting with the Earth's atmosphere, producing secondary cosmic rays, and these secondary cosmic rays are then decaying into tertiary particles, and among those tertiary particles we have neutrinos. And then we have other sources of neutrinos, like we talked about the relic neutrinos, which are again natural sources of neutrinos, and we have seen that their density is quite large, 330 neutrinos per centimeter cube. But today I am going to talk about accelerator neutrinos. And you know that accelerators were developed during 1960s at Stanford Linear Accelerator Center, Brookhaven National Laboratories, and many other places. We have today accelerators at Fermilab, accelerators at LHC is another accelerator, Large Hadron Collider. We have accelerators in Japan, at many places around the globe. And these are high energy accelerators. In India, we don't have high energy accelerators. We have low energy nuclear physics accelerators. And then these accelerators, they are the sources of neutrinos. What's like, if you recall the cosmic rays, what happens? Primary cosmic rays interacts with the Earth's atmosphere, and you have pions and kaons. And then those pions and kaons, they decay to neutrinos and muons and etc. Now here, what we are doing, we are producing proton beam. And that proton beam is striking a graphite target or heavier nuclear target. And from there, pions and kaons, they get produced. And these pions and kaons, being charged particle like pi plus, pi minus, k minus, they are then collimated using a magnetic field. And then when they move, as they have got a finite lifetime, they decay into neutrinos. And those neutrinos, using them, we detect by either putting detectors at the near detector site, which are known as short range accelerator experiments, or to far side, which are known as long range neutrino experiments. Like we have accelerator at CERN, and the detector is in Gran Sasso, which is around 700 kilometers away. We have accelerator in Fermilab, and detector is in South Dakota, which is again a very large distance from there. Therefore, then we have accelerator in Tokai in Japan. This is a place near Tokyo. And then we have a Super Kamiokande lab, which is again a relatively larger distance. It is not short baseline, it is long baseline. Now, then we have also short baseline accelerator experiments. Therefore, we have both short baseline accelerator experiments as well as long baseline accelerator experiments. Besides that, we have also near detector experiments as well as far detector experiments. Now the question is, why so many accelerator experiments presently going on around the globe? As you know, that neutrinos are one of the fundamental particles in the universe, but they are least understood. They play a very important role in our life. As I had told you that when I am putting my thumb like this, trillions of neutrinos are passing through my thumb and I am unable to notice it. But they have played very important role in nucleosynthesis, in formation of light as well as heavier elements that we have talked about. And then they are the sources of information, whether somewhere supernovae has occurred or not. They are sources of information what is exactly going on inside the core of the star, and similarly like that. That is why we talk about these neutrinos. Then if you look at the particle physics also, we have discussed that this universe started with a huge explosion that we call by the name Big Bang, and at that time everything was radiation, and then explosion took place, and matter and antimatter were formed initially. We are living in a matter dominated world, but where those antimatter have gone, it is difficult to tell currently. Either it could be an antimatter universe or a basic phenomena which has eaten up these antimatter. And for this we discuss about CP violation in the quark sector as well as CP violation in the neutrino sector, that is the lepton sector. We know that this CP violation in the quark sector is not enough to understand this antimatter matter-antimatter asymmetry. Therefore, efforts are going on to understand the CP violation in the neutrino sector. Then besides that, we also don't know the absolute masses of the neutrinos. Then the other phenomena that is associated with the neutrinos that we have talked about in brief was the neutrino oscillation. We know that neutrinos come in three flavors: electron type neutrino, muon type neutrino, and tauon type neutrinos. And when they propagate in space, they oscillate from one flavor to another flavor to third flavor, and that is why we had solar neutrino anomaly, atmospheric neutrino puzzle, etc. And we have discussed that these neutrino oscillation is now a well-established phenomena. The important point is that this neutrino oscillation is expressed in terms of neutrino oscillation parameters. And for three neutrino oscillations, we have certain parameters. The important point is to precisely measure these parameters to get information on the CP violation in the lepton sector, etc. Therefore, the important, because what I had told you, that if neutrinos are oscillating, then that means at least one of the neutrino mass eigenstate is non-zero. And that is why it is important to determine delta m square, the difference between, exact difference between, say, mass 2 and mass 3 eigenstates, that is represented by delta m23 square or delta m13 square, etc. Then it is also important to precisely measure the mixing angles that we will talk about. We will talk about Ponte-Carvo, Maki, Nakagawa, Sakata mixing matrix, from where we will see that what are the different neutrino oscillation parameters which the scientists require to measure. Therefore, the important point is that worldwide several efforts are going on to understand neutrino properties. Similarly, I also talked about the double beta decay experiments where people want to see neutrino less double beta decay, where you have two electrons in the final state without producing any neutrinos. And that will tell us about the fact that neutrinos are really Majorana neutrinos. That also we will discuss, because in general, when we talk about neutrinos till now, we are talking about Dirac neutrinos. But if neutrino become their own antiparticle, like pi 0 is its own antiparticle, photon is its own antiparticle, then if neutrino is also its own antiparticle and it has got a mass, It can be a left-handed or a right-handed particle. If it is left-handed, we call it by the name neutrino. If it is right-handed, we call it by the name antineutrino. Therefore, neutrino less beta decay will tell us where there will be lepton violation, will tell us that really neutrinos are Majorana neutrinos. Therefore, the important point is scientists are striving to get knowledge about the neutrinos, and one of the best possible source to get some knowledge about the neutrino properties is through the accelerator experiments, because in the case of supernova, if we talk about when and where the supernova will occur, we don't know exactly. Therefore, we cannot wait all the time. The solar neutrino fluxes, again, these detectors are sensitive to different range of the neutrino spectrum. The flux is not high enough to determine all the things, all the parameters very precisely. Then there are parameters which are sensitive to atmospheric and accelerator neutrinos. Therefore, this is important that we have neutrino experiments in all the sectors, in the low energy sectors, in the medium energy sector, as well as in the high energy sector. Besides that, not only for all this, we also, as I have told you, want to learn about the neutrino properties. And we know that neutrinos are interacting with the target particle. What is the target particle? Target particle is nothing but matter. And matter is nothing but electron, proton, and neutron. Then how these neutrinos are interacting with proton and neutron? They have got a structure. And when we are talking about the interaction taking place inside the nucleus, then that means nuclear medium effects should also come into play, because these nucleons which are inside the nucleus, they are not sitting, they are constantly moving, which we call by the name Fermi motion. Then these nucleons are fermions. Therefore, you have Pauli blocking effects. Then these nucleons are strongly interacting particle. Therefore, you have strong interaction effects. And so on. Therefore, it is important, and that means in the electromagnetic sector or in the strong sector, the information that we get about the hadrons, this is an extra sector, the neutrino sector, which is the weak interaction sector, where besides the vector interaction, you have axial vector interaction also, that we will discuss, that what is the in a few classes, what is axial vector interaction and how we can get information about this axial vector sector using neutrinos. Therefore, about the hadrons, about the interaction of a neutrino with the hadron will give us information about the axial vector sector. Therefore, it is important to perform worldwide experiments using neutrinos, whether it is solar neutrinos, atmospheric neutrino experiment, or accelerator neutrinos, reactor neutrinos, supernovae neutrinos, etc., etc. And what I am talking about is the accelerator neutrinos. What I am telling you, that first you accelerate the protons, which are charged particles, and you know that it is always easy to have the acceleration of charged particles, while you cannot accelerate neutrons, neutral particles. Therefore, these protons then strike the heavy target material, and when they strike this heavy target material, they produce pions and kaons, and these pions and kaons, then they move. These pions and kaons are charged particles. They are first put before the magnetic horns to get collimated, and then they move forward, and when they move forward, then they decay into muons and neutrinos. And these neutrinos we are talking about, either we can place some near detector nearby the accelerator, and then far detectors which are far away from the production point, and that means we are talking about the length of the neutrinos which are traveling. If you are talking about near detector, that means neutrinos are traveling only a short distance, and then you are talking about neutrinos traveling at a distance of 700 kilometers or 300 kilometers or 200 kilometers, so on. That means when we will talk about neutrino oscillation, we will see that neutrino oscillation probability depends upon the length through which these neutrinos are moving. And that is why we have near detector as well as the far detector. And in some of the cases, the near detector and far detector, they are made up of the same material. In some of the cases, they are made up of different materials. Therefore, here you can see that J Park is in Tokai, a place nearby Tokyo. And then you have these pions and kaons which are decaying to neutrinos, and you are placing a near detector here. And then neutrinos are traveling to a distance of about 300 kilometers, and then you are placing a bigger giant detector. This Super Kande has 40 kiloton of water detector. 40 kiloton, you can understand that this will have 40,000 tons, and 1 ton is 10 power 3 kilogram, and that means this will have 4 into 10 power 7 kilogram of material. And then 1 kilogram is 10 power 3 gram. That means this is 10 power 10 gram of material we are talking about. And if you recall the Avogadro number for 1 gram is of the order of 10 power 23, you can see that how many atoms we are talking about inside this, or protons we are talking about inside this water target. Therefore, these really they are giant detectors. And if you recall, when I was talking about the first solar neutrino experiment by Davis, he performed that experiment for almost 25 years because the detector size was not large enough, and he had to wait a few days to have even a single event. And that is why, to have a significant number of events, he had to wait for a very long duration. And that is why he performed that experiment for almost 25 years. And then he reached out to the result that really there is a solar neutrino deficiency, and the number of neutrinos expected from standard solar model given by Behkal et al., that does not match with the experimental observation. That is what we call it by the name solar neutrino anomaly. Now here we are talking about the giant detectors. Now Super Kamiokande is also getting upgraded to Hyper Kamiokande, and the plan is to have a further a factor of 2 almost larger size detector. Similarly, you have another experiment that is planned in United States, that is by the name DUNE, Deep Underground Neutrino Experiment. And DUNE is going to have argon target. Therefore, you have oxygen target, argon target, or scintillators, that is nothing but the carbon target, different nuclear targets. And these different nuclear targets will also give you information about nuclear medium effects in the different nuclear targets. And besides detecting neutrinos, and these neutrinos are called accelerator neutrinos, where they are traveling for almost a distance of 300 kilometers or 700 kilometers or 50 kilometers. That means the oscillation length is quite an important thing for these neutrinos. Therefore, this is what we are talking about. Then recently, in the last one to 2 decades, concept has come for about the off-axis detectors, where the detector is placed at some angle away from the straight line. This red line is showing you the straight line, and that means it is at say 2.5 degree off axis. This is to have a well collimated neutrino beam that we shall talk about in this course, that why off-axis detectors are have been preferred recently, or experiments have been performed using off-axis detector, while we have also on-axis detectors. Therefore, we have both on-axis detectors and off-axis detectors, and that on-axis means this is the production point and the detector is placed somewhere here. Off-axis means that we have tilted this position to a certain angle, say 2.5 or 2 degree or something like that, and then this results in you are losing. See, when you are talking about putting detector at some angle, then that means you will compromise on the amount of the neutrinos those will reach to you. Those numbers will be less, but the energy of these neutrinos which are coming at the off axis, these energies will be in a small energy range, rather in the case of on axis experiments where there will be a broad spectrum. Therefore, it was Ponte Carvo and Schwartz who independently proposed the idea of doing neutrino experiments with accelerators. They proposed the possibility of an experiment making use of a neutrino beam produced by pion decays at proton accelerators. The first accelerator neutrino experiments were performed by a team led by Letterman, Schwartz, and Steinberger in 1962 at AGS Accelerator, Brookhaven. The accelerator facilities are used to accelerate the protons to very high energies. These highly energetic protons are smashed into a heavy nuclear target. Now, because of that collision, a meson carrying electric charge like pi plus, pi minus, k minus can be collimated using electric and magnetic fields known as magnetic horns. Thus, to get a neutrino beam in a certain direction, one points the pion in the direction of the detector. Now, the probability of the meson to decay while traveling a distance L through the decay pipe is given by this expression. Now, the expressions which we are today using, they will be obtained in the class when we will talk about the kinematics, lab frame, center of mass frame, the quantities in the lab frame and the quantities in the center of mass frame. That is a dedicated one unit on the kinematics. But here, just for the completeness, I am writing the expression for the neutrinos probability and what are the mesons probability of decay. This L naught is the pion decay length and is given by gamma beta times the decay time of the meson. This gamma, remember, is the Lorentz factor. Beta is nothing but V by C. When, if you remember, we talk in the special relativity, when we talk about two frame of references, S and S prime, and say this is moving with a velocity V, and you have a particle which is moving with a velocity U in the frame S. Then you obtained all those expressions that what will be the velocity in the S prime frame. And similarly here also we will obtain those expressions of velocity, momentum, force, and other kinematical quantities in both the laboratory frame and the center of mass frame. One S, for example, if we consider it to be lab frame, then S prime will be a center of mass frame, and that will be a dedicated one unit on that. And then this beta, as I am talking about, is the magnitude of the momentum of the meson upon the energy of the meson, and gamma is E meson by M meson. For a 5 GeV pion, the decay length would be around 280 meters. Now, the accelerator neutrinos, the energy spectrum of neutrinos are obtained using the kinematics of the two-body mesonic decay. This we have already done in the class. When the pion decay is at rest, we have obtained the expression. But now, when we are talking about pions moving and then a pion is decaying into a muon and a neutrino, that means these pions are not at rest. And when these pions are not at rest, we have to consider its modified energy and momenta, which here initially was it was at rest. Now, if you consider that, then the neutrino energy, the angle, laboratory angle, and the center of mass energy can be obtained in such way. This will be derived when we will discuss the laboratory and center of mass frame of references. And then using them, since the angle constraint on the angle is between, for cos theta, is between -1 and +1, we can obtain the minimum energy and the maximum energy of the neutrinos. And if you do that, then the different accelerator experiments, those are being performed using accelerators. They are Dune experiment. Dune is going to happen in 2028. Microboon experiment, Minerva experiment, Nova experiment, T2K experiments, and many others. And as you can see, the spectra of these neutrino fluxes, they are not the same. As you can see here, this I am talking about a neutrino from T2K source. Then you have this neutrino from microboon source. This is the flux for the nova neutrinos. Similarly, you have here the fluxes for the dune, planned flux for the dune. This is yet to happen. Then you have the Minerva low energy as well as Minerva medium energy fluxes, etc. As you can see that this T2K flux peaks around 600 MeV, while microboon flux peaks around 650 MeV. Then Nova flux peaks around 2 GeV. Dune flux is also expected to peak around 2.5 GeV, while Minerva low energy peaks around 3 GeV, and high energy or medium energy that peaks around 6 GeV. Therefore, these neutrinos are of different energy. Moreover, since this is an off-axis experiment, therefore the flux is very pinpointed. While if you look at the blue line here, Minerva medium energy flux, this has got a very broad spectrum. Therefore, you have got a broad spectrum for some of the neutrino sources and a peak or very sharp spectrum for the off-axis experiments. Therefore, experiments are being performed both on axis and off axis, and these experiments are being performed both using low energies neutrinos of 500 or 800 MeVs of energy to up to 6 GeV or more than that. Therefore, worldwide accelerator experiments are going on, and people are trying to understand the properties of neutrinos using these neutrino experiments. Let us stop here, and in the next lecture, I am going to talk about cross-section and its physical significance before discussing about neutrino detectors, because cross-section is also a subtle concept which we should first understand the meaning of cross-section, how we define it, then we will talk about the significance, and then we will apply it in the context of neutrino. Let's stop here. Thank you very much.